There is a question that physicists avoid answering in public, not from lack of interest, but because any honest response reveals the limits of what science can reach. The question is simple to formulate. What existed before everything? Before space? Before time? Before the first particle? Before the first vibration of energy? What was there in that non-place that preceded existence? For centuries, this was a question reserved for philosophy and theology, territories where speculation is permitted and even expected. But in recent decades, cosmology has advanced so far that it began to bump against this uncomfortable frontier. Telescopes capture the oldest light in the universe, emitted when the cosmos was only 380,000 years old. The equations of general relativity describe the expansion of space from infinitesimal fractions of a second after the Big Bang. Particle accelerators recreate the energetic conditions of the first instance. And yet, when we try to go back beyond a certain point, beyond the Planck time, that absurdly small interval of 10 to the minus 43 seconds, the equations stop working. The numbers become infinite, the predictions lose meaning, and physics, this extraordinary tool that explained everything from planetary orbits to the behavior of quarks, simply stops. This is not a temporary pause while we wait for better instruments. It is something more fundamental. The very categories we use to describe reality, space, time, cause, effect, may not apply to what came before. And perhaps this is the most profound discovery that modern physics offers us, not an answer, but the clear recognition of where answers end. When you were a child, you probably asked this question to someone. What was there before the universe began? And you probably received an answer that did not completely satisfy, because no answer satisfies. It is not the fault of whoever answered. It is the nature of the question. It seems simple, built with common words. Before exist everything. But each of these words carries assumptions that may not hold when applied to the origin of all things. 20th century physics gave us extraordinary conceptual tools. General relativity showed that space and time are not fixed stages where events happen, but dynamic entities that curve, stretch, and respond to the presence of matter and energy. Quantum mechanics revealed that, at the most fundamental scales, reality does not work as our intuition suggests. Particles exist in superpositions, measurements alter outcomes, and the vacuum ferments with energy fluctuations that arise and disappear continuously. These two theories, each spectacularly successful in its domain, should unite to describe the initial moment of the cosmos, when the entire universe was compressed into a point of unimaginable density and temperature. But they do not unite, at least not yet. Quantum gravity, the theory that should reconcile relativity and quantum mechanics, remains incomplete, a puzzle that the greatest physicists of the last century have tried to assemble without definitive success. This means there exists a region of cosmic history that remains inaccessible to our best theories. We do not know what happened in the first instant, if it even makes sense to speak of a first instant, when time itself may have emerged along with space. We do not know if there was something before, if before is even an applicable category. If the question about what existed before everything is a genuine question or a linguistic error disguised as legitimate curiosity. And perhaps this is exactly what makes this exploration so suitable for a quiet night. We will not solve the mystery. No one has solved it yet. But we can walk together to the edge of knowledge, observe what physics has managed to illuminate, and rest there, at that silent frontier where questions remain open and the mind can finally relax in the vastness of what we still do not know. Before we continue deeper into this journey through the boundaries of physics and existence, I want to say I am glad you are here tonight. If you find comfort in these explorations, if this gentle way of thinking about reality helps you relax, please consider subscribing to the channel and sharing this with anyone who might need something calm and meaningful to accompany them into sleep. These nighttime journeys through the mysteries of the cosmos are created for moments exactly like this one, when you want your mind engaged in something vast and beautiful while your body settles into rest. Whenever sleep feels distant, you are welcome to return here, to let these ideas become familiar companions in the quiet hours. Let us start with what physics actually knows about the origin of the universe, because what it knows is remarkable, and what it does not know is equally remarkable in a different way. The story begins not with the Big Bang itself, but with the evidence that led us to conclude there was a Big Bang at all. In the 1920s, an astronomer named Edwin Hubble made observations that would reshape our understanding of the cosmos. Looking through the 100-inch telescope at Mount Wilson Observatory in California, Hubble studied distant galaxies and noticed something peculiar in their light. The light was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more its light was redshifted. This could mean only one thing: the galaxies were moving away from us, and the more distant ones were moving away faster. Imagine for a moment what this implies. If everything is moving apart now, then in the past everything must have been closer together. Run the cosmic film backward, and the galaxies converge. The universe shrinks. Space itself contracts. Go back far enough, and all the matter and energy in the observable universe, every galaxy, every star, every atom, was compressed into an unimaginably small, hot, dense state. This is what we call the Big Bang. Not an explosion in space, but an expansion of space itself, carrying matter and energy along with it, like raisins in a rising loaf of bread. The evidence for this picture accumulated throughout the 20th century. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, detected a faint microwave signal coming from every direction in the sky. No matter where they pointed their antenna, the signal was there, uniform, persistent, inexplicable by any local source. What they had found, almost by accident, was the cosmic microwave background radiation. The afterglow of the Big Bang itself, light released when the universe was about 380,000 years old and had cooled enough for atoms to form and for space to become transparent. This ancient light is still traveling through the cosmos, stretched by the expansion of space from visible light into microwaves. When we observe it today, we are looking at the oldest light in the universe, a snapshot of the cosmos in its infancy. And this snapshot matches with extraordinary precision the predictions of Big Bang cosmology, the temperature of the radiation, the tiny fluctuations in its intensity across the sky, the ratios of light elements formed in the first few minutes. All of it aligns with theoretical calculations. The Big Bang is not speculation. It is one of the best confirmed theories in all of science. But here is where things become strange. The Big Bang theory describes the evolution of the universe from a very early time. fractions of a second after whatever initiated the expansion. But it does not describe the initiation itself. The equations of general relativity, when run backward, predict that the universe emerged from a singularity, a point of infinite density and zero volume where all the laws of physics break down. The singularity is not a thing that existed in space and time. It is a boundary, an edge, a place where the mathematics produces nonsensical answers and the theory confesses its own limitations. Think of it this way. General relativity is a theory of gravity, and it works beautifully on large scales. Planets, stars, galaxies, the expansion of the cosmos. But gravity is not the only force in nature. At very small scales and very high energies, quantum effects become important. Particles behave as waves. Uncertainty governs position and momentum. The smooth fabric of space-time that general relativity describes should, at the smallest scales, become something else. Perhaps foamy, fluctuating, probabilistic. But we do not have a complete theory of quantum gravity. We do not know how to describe space-time when both gravitational and quantum effects are strong. The Planck scale is where this ignorance becomes critical. The Planck length is about 10 to the minus 35 meters, unimaginably smaller than an atom, smaller than a proton, smaller than anything we have ever probed experimentally. The Planck time is about 10 to the minus 43 seconds, the time it would take light to travel one Planck length. At these scales, our current theories simply do not apply. They were not designed for such extreme conditions. They break down, produce infinities, give contradictory answers, and the singularity predicted by the Big Bang lies precisely at these scales. To understand what happened at the very beginning, if there was a beginning, we need a theory of quantum gravity. We need to know how space-time behaves when compressed to Planck dimensions. And we do not have that theory yet, so there is a wall at the beginning of time beyond which physics cannot see. Not because we lack sufficiently powerful telescopes or particle accelerators, but because we lack the conceptual framework to even formulate meaningful questions about what lies on the other side. The wall is not made of matter or energy. It is made of ignorance, of the gap between what our theories can describe and what reality may contain. As you breathe slowly and let your body relax, consider how remarkable this situation is. We have traced the history of the universe back to a fraction of a second after its apparent origin. We have mapped the cosmic microwave background, measured the abundances of primordial elements, observed the large-scale structure of galaxies distributed across billions of light-years. And yet, behind all this knowledge, there remains a mystery so deep that physics itself must fall silent before it. Not every question has an answer within reach. Some questions may require entirely new ways of thinking, new concepts we have not yet invented. And tonight, resting in that uncertainty is not a burden, but a kind of peace. Let us consider more carefully the word before. It seems innocent enough, a simple temporal relation we use constantly in everyday life. Breakfast comes before lunch, spring comes before summer, childhood comes before adulthood. We navigate the world using this concept effortlessly, arranging events along a timeline that stretches from past to future, with the present as our moving vantage point. But when we ask what existed before the Big Bang, we are using before in a way that may not make sense. and understanding why it may not make sense requires us to rethink what time actually is. In our everyday experience, time feels like a river that flows independent of everything else. Events happen in time, but time itself just is, a fixed background against which the drama of existence unfolds. This was essentially Isaac Newton's view. For Newton, time was absolute, the same everywhere, for everyone, ticking away uniformly whether or not anything happened to mark its passage. Einstein changed this picture fundamentally. In his theory of relativity, time is not absolute. It is woven together with space into a four-dimensional fabric called space-time, and this fabric is not fixed. It bends, stretches, and warps in response to matter and energy. Near a massive object like a planet or a star, time passes more slowly than far away. For an object moving close to the speed of light, time dilates, passing more slowly relative to a stationary observer. Time is not a background. It is part of the physical universe, as dynamic and responsive as space itself. This has a profound implication for the Big Bang. If time is part of the universe, then asking what happened before the Big Bang is like asking what is north of the North Pole. The question sounds grammatically correct, but it may be meaningless. The North Pole is the northernmost point on Earth. There is no north of it, not because something blocks our path, but because the concept of north simply does not apply beyond that point. Similarly, if time began with the Big Bang, then before the Big Bang may be a phrase without referent, a question that dissolves upon examination. Stephen Hawking explored this idea using a concept called imaginary time. In ordinary physics, time is measured with real numbers, 1 second, 2 seconds, and so on. But in certain mathematical treatments of quantum cosmology, it becomes useful to treat time as if it were measured with imaginary numbers, numbers involving the square root of -1. When you do this, something remarkable happens. The singularity at the beginning of the universe smooths out. Instead of a sharp boundary where time begins, you get a rounded finite geometry with no edge, no starting point, no moment of creation. In this picture, asking what came before the Big Bang is indeed like asking what is north of the North Pole. The universe simply is, a self-contained four-dimensional shape with no boundary that requires explanation by something outside it. Time is finite in the past, but has no beginning, just as the surface of a sphere is finite but has no edge. This is a beautiful idea, but it is not the only possibility. Some cosmological models do allow for a meaningful before. In the ekpyrotic scenario, our universe is a three-dimensional membrane floating in a higher dimensional space, and the Big Bang was caused by a collision with another membrane. In this picture, time existed before the collision, and our universe has a prehistory in the higher dimensional bulk. In cyclic models, the Big Bang is just one in an endless series of cosmic expansions and contractions, each cycle giving rise to a new universe from the ashes of the old. In eternal inflation, our observable universe is a bubble that nucleated in a pre-existing inflating space. And that space has been expanding forever, with no beginning at all. Each of these models offers a different answer to the question of what came before. Some eliminate the question by eliminating the before. Others extend time infinitely into the past, replacing one mystery with another. If time had no beginning, why is there something rather than nothing? Why does anything exist at all? And this is where physics becomes philosophy. Because no matter how far back we push the origin, no matter how many layers of explanation we add, we always face the same fundamental question. Why is there a universe capable of having a history at all? Why do the laws of physics exist? Why do they take the form they do rather than some other form, or no form at all? Physics can describe how the universe evolves once it exists. It can trace the expansion of space, the formation of atoms, the birth of stars, the emergence of galaxies. But it cannot explain why there is a universe to evolve in the first place. That question lies outside the domain of empirical science. Not because scientists are too limited, but because the question is not the kind that observations and experiments can answer. So as you rest here, letting your thoughts drift gently, consider this. The word before carries assumptions that may not apply at the edge of existence. Time itself may have a boundary, or it may extend infinitely, or it may be something stranger still, something our current concepts cannot capture, and not knowing the answer is not a failure. It is simply where we are, at this moment in the history of human understanding, gazing at a horizon we cannot yet cross. There is a picture that physicists sometimes use when they try to imagine what space-time might be like at the very smallest scales. They call it quantum foam. The name evokes something bubbly, churning, dynamic, and that is roughly the idea. At distances far smaller than atoms, far smaller than protons, down near the Planck length, space-time may not be the smooth, continuous fabric that general relativity describes. It may be turbulent, fluctuating, uncertain, a froth of quantum activity where the very concepts of distance and duration lose their ordinary meaning. This is speculation, but it is informed speculation, grounded in what we know about quantum mechanics and gravity separately. Quantum mechanics tells us that at small scales, nothing is definite until it is measured. Particles do not have precise positions. Fields fluctuate even in their lowest energy states. The vacuum is not empty, but seethes with virtual particles popping in and out of existence, borrowing energy from the uncertainty principle and paying it back before anyone notices. Gravity, on the other hand, tells us that space-time is not a stage, but an actor. Mass and energy curve space-time, and that curvature is what we experience as gravity. But if space-time is physical, if it responds to energy, then at the quantum level, it should also be subject to quantum fluctuations. It should jitter, it should foam. John Wheeler, one of the great physicists of the 20th century, coined the term quantum foam in the 1950s. He imagined that at the Planck scale, space-time would be riddled with tiny wormholes, bubbles and topological complexities, a seething chaos where the smooth geometry of Einstein's equations would be replaced by something far more exotic. In this view, the space-time we experience at ordinary scales is like the surface of the ocean seen from an airplane, smooth and calm. But zoom in close enough, and you find waves, ripples, spray, turbulence. If this picture is correct, then the question of what existed before the Big Bang becomes even more complicated. Because at the Planck scale, near the supposed singularity, time itself may become ill-defined. It may fluctuate, it may branch, it may not flow in a single direction or any direction at all. The very framework we use to ask about before and after may dissolve into quantum uncertainty. Some approaches to quantum gravity take this idea seriously. Loop quantum gravity, for instance, suggests that space-time is not continuous, but made of discrete units, tiny loops of gravitational field woven together like a fabric. In this picture, there is a minimum length and a minimum time. You cannot have distances smaller than the Planck length or durations shorter than the Planck time. The singularity predicted by classical general relativity is avoided because space cannot be compressed to zero volume. Instead, as you approach what would have been the singularity, quantum effects become strong, and the universe bounces, contracting to a minimum size and then expanding again. In loop quantum cosmology, the Big Bang is replaced by a big bounce. Our expanding universe emerged from a previous contracting phase, and time extends infinitely into the past through an endless series of expansions and contractions. There is no beginning, no first moment, no creation event. Just an eternal oscillation, each cycle giving rise to a new cosmic epoch. String theory offers a different perspective. In string theory, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. These strings require extra dimensions of space beyond the 3 we observe, usually 6 or 7 additional dimensions, curled up so small that we cannot detect them directly. In some versions of string theory, our universe is a 3-dimensional membrane floating in a higher dimensional space, and the Big Bang was caused by interactions between membranes. But string theory has not yet made definitive predictions about what happened before the Big Bang. The mathematics is extraordinarily complex, and there are many possible versions of the theory, many possible configurations of the extra dimensions, many possible ways the initial conditions could have been set. String theory offers a rich landscape of possibilities, but not, so far, a unique answer. What all these approaches share is the recognition that our ordinary concepts may break down at extreme scales. Space and time, the most basic categories of physical description, may be emergent rather than fundamental. They may arise from something deeper, something we do not yet understand, something that does not look like space or time at all. Think of temperature. Temperature is a real property of physical systems. You can measure it, predict how it changes, use it in calculations. But temperature is not fundamental. It emerges from the statistical behavior of many particles. A single molecule does not have a temperature. Temperature only makes sense for collections of molecules large enough to have meaningful averages. Perhaps space and time are similar. Perhaps they emerge from some underlying structure that is not spatial or temporal, quantum information or entanglement, or something we have not yet conceived. If so, then asking what existed before space and time is like asking what existed at temperatures below absolute zero. The question assumes a framework that does not apply. This is a humbling thought, but also a liberating one, because it means the mystery at the beginning of the universe is not a failure of physics, but a signpost pointing toward deeper truths. The questions we cannot answer today are invitations to think more carefully, more creatively, more humbly about the nature of existence. And as you lie here, breathing slowly, you can let these questions float in your mind without demanding answers. They are companions for the journey into sleep, not puzzles that must be solved before you can rest. We have arrived at what may be the deepest question of all, a question that physics cannot answer, that philosophy struggles to address, that has occupied human minds for as long as humans have been capable of wonder. Why is there something rather than nothing? At first glance, this question might seem trivial or even meaningless. Of course there is something. We are here after all. The universe exists. Stars shine, planets orbit, life evolved. And here you are, listening to these words in the quiet of the night. The existence of something seems like the most obvious fact imaginable. But when you really stop to think about it, when you let the question sink in, it becomes deeply mysterious. Consider what nothing would mean. Not empty space. Empty space is still something. It has properties. It can expand. It contains quantum fields in their ground states. It obeys the laws of physics. True nothing would be the absence of space itself, the absence of time, the absence of laws, the absence of any structure or pattern or regularity whatsoever. No dimensions, no properties, no potential for anything to happen, because there would be no framework within which happening could occur. Now ask yourself, why is there not that? Why is there this vast, intricate, law-governed cosmos instead of absolute nothing? Why do the laws of physics exist? Why do they take the particular form they do? Why is there something that can ask why there is something? Some physicists have tried to address this question. Lawrence Krauss, for instance, wrote a book called A Universe from Nothing, in which he argued that quantum mechanics allows the universe to arise spontaneously from nothing. In quantum field theory, the vacuum is not truly empty. It is a seething sea of virtual particles and field fluctuations, and in some speculative models, the entire universe could have emerged as a quantum fluctuation from a pre-existing vacuum state. But this does not really answer the question, because a vacuum state governed by the laws of quantum field theory is not nothing. It is a very specific something, a quantum field in its lowest energy configuration, obeying precise mathematical rules. To say the universe arose from this vacuum is to presuppose the existence of quantum fields, the laws that govern them, and the mathematical structures that make those laws coherent. Where did all that come from? You can push the question back further. Perhaps the laws of physics themselves emerged from some deeper structure. Perhaps there is a more fundamental theory, a theory of everything from which our known laws derive. But then where did that deeper theory come from? Why does it exist rather than some other theory, or no theory at all? This is what philosophers call the problem of ultimate explanation. Any explanation you give for why something exists will itself involve something. A law, a principle, a structure, a cause. And you can always ask why that something exists. The chain of explanation either goes on forever, which seems unsatisfying, or it stops somewhere, which seems arbitrary. Neither option feels like a complete answer. Some thinkers have suggested that the question itself is somehow illegitimate. Perhaps asking why there is something rather than nothing is like asking what is north of the North Pole, a question that seems meaningful but actually is not. Perhaps existence is just a brute fact, something that simply is without explanation or justification. The universe exists because it exists. There is no deeper why. Others have proposed that every possible universe exists, that reality is a vast multiverse containing all logically consistent configurations, and that we find ourselves in this particular universe simply because it is one of the possibilities. In this view, the question of why there is something rather than nothing becomes trivial. There is something because nothingness is not a logical possibility, or because every possibility is realized somewhere. But even this does not fully satisfy, because you can still ask why there is a multiverse, why logical possibility translates into actual existence, why the framework within which these possibilities exist is the way it is. The question has a way of surviving every attempt to dissolve it. And perhaps this is the deepest lesson physics has to teach us about the origin of existence. There are limits to what science can explain. Physics is extraordinarily powerful. It has given us the Big Bang, the cosmic microwave background, the standard model of particle physics, the expansion of the universe. It has explained phenomena from the behavior of subatomic particles to the large-scale structure of the cosmos. But it operates within a framework, the framework of laws, mathematics, space, time, causation, and it cannot explain why that framework exists in the first place. This is not a criticism of physics. It is simply a recognition of what physics is and what it does. Physics describes how the universe works, not why there is a universe to work. The why question lies outside its domain, in the territory of philosophy, theology, or perhaps in a domain of thought we have not yet invented. So, as you rest here in the quiet of the night, you can let this question settle over you like a soft blanket. Why is there something rather than nothing? You do not need to answer it. No one has answered it, but you can hold it gently, as a reminder of how deep the mystery of existence goes, how much remains unknown, how small our current understanding is compared to the vastness of what might be understood. And in that vastness, there is a kind of peace. The mystery is not a problem to be solved, but a wonder to be appreciated. You are part of it, a small piece of the something that exists rather than nothing, and that is remarkable enough. There is a temptation, when confronting the limits of knowledge, to feel frustrated or anxious. We want answers. We want explanations. We want to understand. And when understanding proves impossible, when we reach the edge of what can be known, there is a natural tendency to push harder, to insist that there must be an answer somewhere if only we look hard enough. But there is another way to respond to mystery. Instead of frustration, we can cultivate a kind of peaceful acceptance. Instead of anxiety, we can find wonder. Instead of insisting on answers, we can learn to rest in questions. This is not the same as giving up or abandoning the search for knowledge. Scientists continue to work on quantum gravity, on cosmology, on the foundations of physics. Philosophers continue to wrestle with the deepest questions about existence and meaning. The quest for understanding is valuable and should continue, but alongside that quest, there is room for a different attitude, an attitude of appreciation for the mystery itself, independent of whether it will ever be solved. Consider how it feels to look at the night sky. The stars scattered across the darkness, the faint glow of the Milky Way, the knowledge that each point of light is a sun, perhaps with planets, perhaps with life, stretching across distances so vast that light takes years, centuries, millennia to cross them. There is something deeply peaceful about that contemplation, and the peace does not depend on understanding everything you see. It comes from the encounter with vastness, from the recognition of how much more there is than you can comprehend. The question of what existed before everything, of why there is something rather than nothing, is like that. It is an encounter with the vastness of existence, with the depth of the mystery that underlies everything you experience. And you do not need to solve it to appreciate it. You can simply stand at the edge of the known, look out into the unknown, and let the immensity of it all settle into your bones. There is a long tradition in human thought of finding peace through the acceptance of limits. The ancient Stoics taught that tranquility comes from recognizing what is and is not within our control, and that wisdom lies in focusing on what we can change while accepting what we cannot. The contemplative traditions of many cultures emphasize the value of unknowing, of emptying the mind of its constant grasping for certainty and resting in the openness of not knowing. Physics, surprisingly, points in a similar direction. It shows us that the universe is far stranger than common sense suggests, that our intuitions about space and time and causation break down at the extremes, that the deepest questions may lie forever beyond the reach of empirical investigation. And this is not cause for despair. It is cause for humility, for wonder, for a kind of reverent acceptance of the mystery in which we find ourselves. Tonight, as you prepare for sleep, you can practice this acceptance. You do not need to figure out what existed before the Big Bang. You do not need to solve the problem of why there is something rather than nothing. You do not need to reconcile quantum mechanics with general relativity or discover the theory of everything. These are tasks for future generations, for minds not yet born, for a humanity that will continue the quest for knowledge long after you and I are gone. What you can do right now is rest. Rest in the mystery. Rest in the not knowing. Let the questions float in your mind like clouds drifting across a sky, present but not demanding, beautiful in their indefiniteness. The universe is vast and strange and largely unknown, and you are a small part of it, a brief flicker of consciousness in the cosmic dark. But that flicker is precious. That flicker is aware. That flicker can contemplate its own existence and wonder at the mystery of why anything exists at all. And as your breathing deepens, as your body relaxes, as your thoughts begin to slow and soften, you can let go of the need to understand. Understanding is wonderful when it comes, but it is not necessary for peace. Peace can come from acceptance, from wonder, from the simple recognition that you are here now, part of this mysterious something that exists rather than nothing. And that is enough. The stars continue to shine whether or not you understand them. The universe continues to expand whether or not you can explain it. And you continue to exist, breath by breath, moment by moment, a small conscious presence in the vast unconscious cosmos. There is nowhere you need to go, nothing you need to figure out, no problem you need to solve before you can rest. The mystery will still be here tomorrow. Tonight, you can simply be. And so we arrive at the end of this journey, though perhaps end is not quite the right word for a journey through questions that have no end. We have walked together to the edge of what physics can explain, to the wall at the beginning of time, to the place where equations fall silent and concepts dissolve. We have seen that the question of what existed before, everything may not be answerable, not because we lack cleverness or data, but because the question itself may assume a framework that does not apply to the origin of all frameworks. We have considered the possibility that time is not a background against which events occur, but a part of the universe itself, something that may have a beginning, or may not, depending on how reality is ultimately structured. We have glimpsed the quantum foam, the seething uncertainty at the smallest scales where space-time itself may lose its familiar form. We have confronted the deepest question of all, why there is something rather than nothing, and recognized that this question may lie forever beyond the reach of scientific explanation. And through all of this, we have practiced something valuable: the art of resting in mystery. Because not all questions have answers, and not all mysteries need to be solved. Some of them are simply part of the landscape of existence, features of the territory we inhabit, wonders to be appreciated rather than problems to be eliminated. You are lying here in the quiet of the night, a conscious being contemplating the limits of knowledge. That is remarkable. That is worth appreciating. Whatever existed before everything, if anything existed, if before even makes sense, led somehow to this: a universe that became aware of itself, that began asking questions about its own origin, that can lie in the dark and wonder. And now, as sleep approaches, you can let all of this go. The questions will remain patient, unchanged, waiting for you or for someone else to return to them another time. But you do not need to carry them now. You can set them down, gently, like setting down a book you have been reading. The story continues, but you do not need to read it tonight. Breathe deeply. Feel the weight of your body against the bed, the softness of the pillow, the quiet of the room. The universe is vast and ancient and mysterious, and you are a small part of it, resting now. Letting go, drifting towards sleep. There is nothing you need to understand before you can rest. There is nothing you need to solve. The mystery is not a burden. It is a gift, a reminder of how much more there is than we can comprehend, how deep the cosmos goes, how strange and wonderful it is that anything exists at all. Sleep well, rest deeply, and when you wake, the universe will still be here, still mysterious, still beautiful, still waiting to be explored. But for now, let it all go. Let the questions fade. Let the mystery hold you gently as you drift into the darkness, into the quiet, into the peaceful unknowing of sleep. Good night.